Okay. So hello. Yeah, I'm Per. I'm speaking about and working on mainly on the Erlang parts at the moment, on the embedded parts and these demo things. And this is.
I'm Claudia Doppioslash, and I'm working mainly on the Elm parts.
Yeah. Let's start. So Elm and Erlang. So first, I want to talk a little bit about where I basically come from or how I got to Erlang. That's also a embedded device. It's a little bit larger. It's a flashing tool for the automotive industry. All the automotive stacks are written in Erlang. For the third version, I switched to Erlang because I was bored doing it again in C and liked a lot the productivity gains of Erlang, and this was the product was. And back then, it was like a little bit more traditional. There was a main board running FreeBSD where the Erlang stuff ran, and it was connected over USB to some automotive gateways, which did all the low-level automotive stuff. So I basically had some like just queuing gateways doing the low-level stuff, and Erlang was only talking to the USB. For the more embedded applications in industrial control systems, we needed some more compact hardware, and also we need more control over our timing and real-timeness. And so basically what I did is I ported Erlang to a smaller hardware and a hard real-time operating system. And out of this came basically the need that the users who actually build these industrial control systems also want to program them. But they are not used to programming Erlang. They won't touch Erlang. They won't even touch C or whatever. They are in their own world. They are different, separate kind of software developers, and that's why I have to introduce the field a little bit, because you probably have no connection to those people. Did anybody in the room ever program a PLC? Ah, you don't count. Oh, another one, 2, 3. Yeah, top. So I hope I have something new for you too, because it's actually a new kind of PLCs. So what is a PLC? Programmable logic controller. These have like 30 years of history or even more. They were invented basically to replace having to rewire the whole control station by an electrician every time when you want to change the process. So they wanted to have some kind of programmable wiring, and that's basically the first standard that came out was like looking like the diagrams which the electricians draw how to do the wiring. You had relay and delays and all kinds of this stuff. And this evolved for 30 years, and now there's a plethora of different ways to program these, and most times they are just boxes with lots of I/O. And currently there's a normal computer in them, sometimes even a rather large computer if you need a huge PLC that does lots of stuff, because the way they actually work is kind of inefficient, because a normal PLC, you write a program and it runs in circles. And that's a cycle time. That's your real-timeness, basically. Your program runs in circles. And if your circle time gets too slow because your program gets too large, you need a larger PLC. But it always runs. And so nowadays we want to like have stuff more distributed and more networked, and also like have computers that do other stuff than the PLC. So there is a new standard for PLC, that's IEC 64099. It's a quite new standard by PLC things. It's like post-2000. And what they added there is it doesn't run in cycles anymore, but it also has a data type for events. And I just picked out a block. It's basically, we don't have time to introduce it all. So lots of the PLC languages are graphical. So you have basically blocks and you wire them together. The modern ones, and you have I/Os. So links on the left side, there are the inputs, on the right side, there are the outputs. And the new standard added basically the thing on the top, that it has a little head on the top, and the thing on the top, there are actually events. So real events, not like being switched on for 10 milliseconds and then switched off and triggered for this, but a real event, like point in time. And the I/Os are basically connected to the events and only valid and sampled when the events is. So for the embedded system, I ported, for this control system, I ported Erlang to Artems. Artems is an open source hard real-time operating system. It's actually saying operating system is a little bit much because it's actually an executive. So you link your whole operating system to your application, and you have one image, and you run this. And you run on the hardware, you can access every bit in the hardware, there's no memory protection, there are only threads. No processes, nothing. And basically the application here is the Erlang VM linked together with the operating system, and some drivers to actually access the hardware, basically linked to the whole thing, and you can access them from Erlang. So with this, I get basically advantages to have all the things. Erlang, I don't know, I probably don't have to introduce Erlang first. Erlang is a mostly functional language, which has also a kind of process model, which is that shares nothing with the other processes. So that's actually a much improvement over the threads we have embedded systems. We do message passing between those processes, and they are very lightweight, and we can have many of them. And it's also failure tolerant, and you can do hot code upgrade, and that's actually features very interesting industrial control systems, because you don't have to stop the conveyor belt to upgrade your system. And failure tolerant is also very important for the customers, because yeah, when the thing stops, manufacturing stops, and then you get angry calls. Yeah, okay. This project is like ongoing for a while. It's called GRISP. It's in theory open source. Actually, it will be like committed back to the Erlang OTP, and I'm in the process of actually finally finalizing it, because having a budget now actually helps. So I want to show a little bit like how these modern languages for PLCs look. This is one of the highest level languages. There are like assembler-like languages. There's a whole set of languages, all standardized. And this is the language for writing a function block for one of the modern distributed PLCs. So you have you start a function block. That's basically then one of the blocks that basically the technicians can just write together and apply something. This is actually the source code of the block that runs on this traffic light we will show afterwards. So you basically declare your event inputs. You declare the this thing is connects to data. Then you have your data inputs and your data outputs. And on the next slide, there's basically a built-in. Oh, actually, this is cut off a little bit. Yeah, too late to adjust. So there's a first line that you don't see, which just says it's EC states. So you have a state machine built into the thing. It's basically a hardwired, quite complex state machine where you have states. The states basically run algorithms. That's the thing with alg. So if you enter the state, you run some piece of code, and you can trigger output events. That's the thing after the arrow. It's details. Then you have transitions between those events, basically triggered either. Basically always trigger by an event. If you don't receive an event, you just sleep. You do nothing. So it's not running in circles anymore. Very efficient now. Just waiting, sitting there and waiting. Actually, that's what an Erlang process can do very well. And there's, if an event comes in, there's basically the transitions go, this is basically an event here. So you can basically trigger on an event, or you can have an event and a condition, or only a condition. But the condition is also only checked when any event comes in. It's just not dependent on any specific event. So yeah, also details. And then finally you have the algorithms. That's, in this case, we just set the output lines basically to have the right traffic light patterns, and the transition machine actually triggers the output event, which actually makes it happen in the hardware. So in practice, this is only wired to some delay blocks and to the IOs. That's all we have at the moment. So why did we actually build this? The application is a research project currently. So we have a little bit more freedom of what we implement, and be a little bit more progressive what we want to do, because it's not only halfway customer budget. This is basically the Smart Fit project. It's a German research project. And my customer is Bosch Rexroth, who is actually partner in this research project, and they are building, basically, we're trying to build the next generation of manufacturing control systems with all kinds of, yeah, it's called Industry 4.0, whatever it might mean. I don't know what Industry 2.0, 3.0. Actually, there's a definition, but I can never remember it. It's 4.0 now. That's what we do. If you want to be on the front edge, you do 4.0, whatever. And yeah, we wanted to have programmability by PLC programmers, because we Erlang programmers didn't want to do all the machinery setup by ourselves. I mean, there's lots of machineries, and there's only 2 of us. So yeah, that doesn't work. And I've brought a few pictures. That's basically these boards in a actually largish box. It could be smaller, but it was for a research demonstrator. They put a little bit larger box on it because they had put lots of files in it. It was shown on CeBIT. That's up there you see a transport system, the demonstrator. That's a box around these boards. So these are the actual boards. Actually, they are old boards. I also brought the video. So that's what the thing does. You have little pallets where the product is on, and it gets moved around, and the lifts go up and down, and you have kind of sensors all everywhere which detect if there's something coming, and you have all kinds of actuators. And this is actually controlled by the PLC language, by these function blocks, which I wrote a compiler for, which compiles to Erlang processes. So underneath we have Erlang processes basically. It's beam files that comes out of it. And yeah, you need to like have RFID reader. This thing also has a RFID reader connected. That's actually how we started. And you need to like fix the product, and that's about it. I think it's done, yeah. Next slide. So this is how it looked on CeBIT. It was like shown on CeBIT last year. Initially it was planned to go on Hanover Trade Fair this year, but I don't think we have funding for this. And with this slide, let me a little intro. So why do we need Elm for this? The PLC programmers, they are used to a graphical IDE basically. They want blocks, and they occasionally write source code like what's in the block, but on the high level stuff you wire blocks, like electrical or like MATLAB or something like this. It's very similar. So they won't touch if you say yeah, use Emacs and here's your source code and there's the compiler, build your stuff, they won't touch it. And if you make them touch it, they will hate you. So we need an IDE, and the idea was basically to put the IDE not on a Windows computer where it normally runs. You have to install a large IDE on the Windows computer, but to actually put the IDE in the embedded system, since the compiler is already written in Erlang, and actually quite compact because it's Erlang, it has quite compact code, it actually fits easily in the embedded system. So the compiler runs on the embedded system also, and what we need is an IDE to actually show stuff. And what do if you want to have a portable IDE nowadays? You do Web-IDE. And for this Web-IDE, we also wanted to do something innovative, and that's where Elm comes in. And now I hand over.
So I'm going to give you a very short overview of Elm. Who here has already done Elm or played with it or is familiar with it? So I'll keep it short. So Elm is a purely functional language, so immutable, basically. And it's based on functional reactive programming. If you're familiar, we might be familiar with the reactive, but it's basically how spreadsheet works. So if you have a value B that depends on a value A, whenever the value A is updated, the value B is also updated, which is very good, I think, for UIs, for example, which is what we're using it for. And then it's an eager language, so if you have a lazy language, then your value is only evaluated, your variable is only evaluated when you actually need it, but that's a bit unpredictable. You can have space and time leaks, which are not good for embedded real-time devices or games. So an eager language is better for this. This type system is static and it's quite expressive. Since it's purely functional, you have to model the side effects. So it really keeps you in check and makes you think about where you're using side effects and how to do it properly. It compiles to JavaScript, HTML, and CSS, mostly JavaScript really, and it's very good performance for rendering, especially HTML, because it uses virtual DOM, which is a very fast library. And if you look at line, there are tests where it shows it's quite faster than Ember.js and other stuff. It interoperates with JavaScript while still being type safe, so it manages to keep JavaScript in its own box and make it not do too much damage. Also, since the type system is very good, you rarely encounter runtime exceptions, which is the main advantage. So your work is all up front, basically. Once it compiles, much like Haskell, it runs. It's still a small language, so you will be able to put it all in your head. It's not like C++ when all everyone ever does is know their own bit and they never know the other bit. So it's small, it's good. It was invented by Evan Zaplicki for his thesis just in 2012, so it's pretty recent. It's meant to be approachable and practical, so the community is very focused on making it useful for people, and it's already used in production in various companies as a testament to that. Also, it's very careful about what terms it introduced, so it won't tell you, it won't have things like monads. It will do everything quite slowly, so it's like, please don't adopt me because I won't scare you off with terms that might be scary. It's in production at these companies, and a couple more have in this company as well, and a couple more as well. So there's quite a thriving community. And then I should give you the microphone again.
Yep. Okay, so we basically introduced the technology we want to use on the front end for the IDE. The IDE needs to talk to the back end, basically. And what we actually want to have, if you want to debug a real-time machinery, you actually want to have real-time display of the values in the machine, like in your function blocks. So normally you show function blocks and you have little numbers. What's the current number? What's the state machine doing inside the function block? You have a little diagram, the state changing live, basically. And you also want to have like kind of like having like little scopes where you could use look at the timeline, what just happened, but also this should update immediately, because normally you would stand at the machinery and something happens and you said, whoa, 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 what's happening there? Oh yeah, this value is wrong. So you need to be basically, you need to sync the physical world while debugging with because usually you're debugging the physics. So the mechanics is too slow or too fast or whatever, and it jumps off the rail because you move the lift too fast, and you need to fiddle with the milliseconds a little bit. And so that's why it's very important that you can actually see which state, or sometimes it just locked, it just doesn't move anymore. Why doesn't it move anymore? What's the state? So I need fast update of state. And so I need some way of bidirectional connection, and we have a web interface now, and we want a lightweight, because it's an embedded system, and low latency communication between the things, because we might have to update lots of values. If you look at the big diagram, lots of stuff is changing all the time. So there's actually some cause for efficiency. Traditionally, there was like there were several ways to abuse HTTP to actually get live updates from the server. It's long polling. You probably heard about it. You basically make an HTTP request, and the server doesn't answer it right away, but it like keeps waiting until it has an update, and then it suddenly answers you. And it lets the connection time out, and the client does a next connection. And so this is kind of only half of the solution, because you basically, if you are having one connection waiting, and the client actually wants to tell the server urgently something, it has already the one connection waiting. So you usually have then multiple connections, basically two, like one for pushing to the server and one from getting fast updates from the client. And then you have the mess that you have a request on the one thing, and you have to match up your answers on the other thing, and it's a big mess. So and then you have to implement normally everything in JavaScript. It makes the mess not smaller but larger. And so yeah, it was not fun. So there was some new solution, which is called Websockets, which I shortly will introduce. I'm not sure if everybody heard of it. There's a RFC for it. So there's actually an IETF standard. It's a protocol standard, not only a V3C standard. So this is usually more solidly specified also. It mainly works that you have if you have a WebSocket connection, it's a normal HTTP connection. So it starts normally, and then you have a special header going on, which I will shortly show, which then upgrades your connection to a WebSocket. And then the server answers with a similar header, and then from then on, you have a TCP connection between the client and the server. And there is only some minimum framing going on. You have frames on the TCP, so you don't have to like look at the packets. You have your own frames, and these frames are automatically assembled by whatever library or the browser to messages. So you have basically message passing. You can shove in messages at both times, in both sides. You have a bidirectional connection. It's only one TCP connection. It doesn't need to reconnect all the time, and especially it doesn't need to send an HTTP header on every long poll, and which is quite inefficient. I mean, for example, if we want to show values, we actually only need a few bytes to actually transfer a value. It's like, and that's like a factor of 1,000 larger if you have a large HTTP header every time. And you might have a new TCP connection and whatever. So this is much better. It goes over port 80, so it normally proxies can't mess with it as well as they, it goes through the firewall basically. It's not an issue for us because normally all this stuff should be behind the firewall and not be accessible from the outside, hopefully, because you can actually reprogram the PLC with over the IDE. So you might not want to have somebody from outside remotely programming it, except if it's a technician, and that's probably one of the interesting things to secure then. So I show shortly how this looks. That's an HTTP header, and that's the client handshake. The client does a GET request on some URL. It has a host field that it's basically if you have virtual hosting, it's a host field you want to connect to. And then you have basically two things: upgrade WebSocket and connection upgrade. So connection is a standard header field, and the upgrade WebSocket is basically the upgrade header special thing. So basically with the one you tell it you want to upgrade the connection, and the other tells it to what. So we want WebSockets. And then you have some kind of random thing going on here. This isn't actual security. That's just a feature to basically get around proxies messing with your connection. Because a proxy might think he's smart if you reconnect to your WebSocket again and said, oh yeah, I saw this all. I have it cached. I'll send you what you got last time, and then you get a replay of your last connection. You don't want this. You want a new connection, of course. And therefore, you send basically a random string to the server, and what the server does with it we see in the next slide. And you have origin, and then you can basically have like internal stuff that to say what sub-protocols. There can be sub-protocols in WebSocket, so that's already complexity being slapped on, as it's usual. So you can have basically, it's an extensible framing protocol where you can do all kinds of extensions with it. And of course, there's a version field, and the server answers with this. It says, yeah, fine, let's switch protocols, let's upgrade to WebSocket, I agree. And it also sends back a random thing, which is basically made from the other random thing the client sent, attaches a known kind of unique thing. It's a UID, which is basically in the standard. It should not be like by random in any proxy. So it attaches to it, and it does as SHA digest and sends this back. So this is not security. Nothing to do with security. It's just like prevent stupid old proxies fooling with it. Because a new proxy basically should say, oh yeah, WebSocket, I stay away. But an old proxy, there are tons of old proxies around, and they would mess with it. And with this, you would at least detect it that this is wrong, something's wrong. I didn't get my connections. Then you drop the connection, and then you can have a fallback or whatever. So with the WebSocket, we go to the Erlang side. And on the Erlang side, there are several choices of web servers, and one of the web servers is Cowboy, which is kind of widely used. And the advantage of Cowboy that it has built-in WebSocket support that kind of we need. So the choice was easy because I think the other web servers were either larger or didn't have WebSockets. And there's also, by the same author, by Loic, a library called Bullet, which basically gives you the both ends of the WebSocket, the JavaScript end, like a basic library for actually opening WebSockets, and an Erlang end, which is actually compatible with each other. So they immediately talk to each other, which is kind of convenient. And the JavaScript side also has, or both sides also have a degrade of connection, basically. If you can't have a WebSocket, it also can support event source, which was kind of the predecessor of WebSockets and didn't take off well. So it's actually kind of deadish. So probably I wouldn't recommend using this anymore. So rather use WebSocket. But if you have an old server, actually Bullet can automatically downgrade to event source for you transparently. And it can also do long polling if nothing else works. It just long polls for you. This gives you a limitation because your transport needs to be text then. So you could basically do binary-only WebSockets because WebSockets support this, which is kind of neat. But if you want to be able to take have the use of the long polling or the downgrade, which is also kind of nice, you probably stick to text. and have some kind of efficient text encoding. So if it finally arrives on the Erlang side, what you basically need to provide to Cowboy basically is to Bullet actually. So you plug in Bullet as a general connection handler on your path, and then you need to have a module which actually handles the Bullet connection. And this is a kind of simple callback module. If you're familiar with Erlang, it's looks like similar kind of like Gen server or whatever. That's the way of Erlang encapsulating the complicated process stuff and the state stuff, and you only have to provide a callback module which is functional. And then you can test it functionally, for example, because you're only testing the state is hidden away in a different module. And that's what Bullet does. You have an init, which is basically every time called when there's a new connection. And you need to be aware that you always can get a new connection anytime, because the connection might drop all the time, or if it has to fall back to long polling, you will be getting a connection every time. There won't be anything staying. And for this, it's actually the active field there. It actually tells you that you are active once. That only sent me one message because I can't deal with more. I have to close the connection after the message because I'm actually long polling. And but if this is not active, normally there's a process staying in the web server, being active as long as the connection is there. And this process basically sends you, if something's arriving on the stream, like a message input, you get a stream callback where you have basically your data. And then you can do, in the dots, you can do whatever. In the init, you set up your state, basically. Usually, you connect to a session process or something. You have some kind of other process that you control, which always runs, which keeps your session state encapsulated. And in the init, you basically look the session process up by a session ID, for example, or just by a fixed name if you only have one. And you basically tell your session process, oh, we have a new connection, and I'm the new connection process. Talk to me from now on, for example. And in the stream, you basically get your data. You can do some processing. And the request is basically a thing that Cowboy has in every call. It's basically the HTTP request, so you have to pass it around all the time. It's kind of annoying. And I think Loic is working to get rid of this in the next version. But it basically handles the connection state, the web server state. And the state is actually your state. You get passed back your state, which you basically created in the init. And you also reply with it. If you got something, you say, okay, you get the request, and you can update your state and pass it back the updated state, so you can keep your state updated. And there's another callback that's called info, which is basically whenever the bullet process, the connection process, gets some Erlang message from outside, this callback gets called, and you get the message. That's basically, actually I kept, this is wrong, I kept the message in now, it's a refresh message, but there's actually some data, it's a message. Your message, you sent it to it, your session process probably sent it. So you get the info, you get also your state and the ubiquitous request request data. We don't have objects in Erlang. And you reply, you have several replies here. You can also reply with OK, which basically saying, yeah, okay, I take care of it, but I'm not sending anything now. Or you do a reply, which basically sends a message on the WebSocket. So this is basically the way the messages go back to the client. And there's also a terminate callback, which you can tell your session process, I'm no longer, we're tearing down the connection, we're rolling it up, and please no longer talk to me. Wait for the next connection process. And it's actually kind of neat. They actually didn't forget in WebSockets that there's actually in-band a message that you're about to close the TCP connection. So the client basically, or each side can say, oh, let's close it, like in-band. So the TCP connection is still there. And only if both say close, then you normally close. I mean, you can always pull the plug and then it just goes away. Distributed system. Network is not reliable. But if everything works well, they talk to each other, because there is a problem if you just close a TCP connection. You have stuff buffered in the TCP chain, and if the other side closes too early, it basically loses data. And the close message is basically a kind of tag behind your data, which basically tells the other side, if you see this close message, I've sent you everything I wanted to send you. And that's when your terminal gets cold. And also when the connection goes just away. Oh, demo, yeah, already demo time, okay. So you can probably see the demo well, or yeah, I think you can see it. So what we have here is two of the embedded boards. It's actually the same boards that control the industrial transport systems, just a little bit old version. They're connected by Ethernet, so we have a distributed system because it's a distributed PLC language. We need a distributed system, so we need at least two boards. And it's also one, there are little switches on the boards. There's also one connection going to this laptop, which we probably should connect now. Let's switch screens and hope everything works. Hello? Better give some time. It's probably confused because I just switched. Oh, it's gone loose. Thank you. Much better. So you're supposed to see something soon. Yeah. So let's move the window a little bit in the middle. So what have we here? We have the two embedded systems, and the application we do is traffic lights. And since normal traffic lights would be kind of boring, we also have a sensor. So it's a sensor traffic light, like one of those who basically are red, and as soon as you drive with your car to the traffic light, it basically detects your car with a magnetic sensor in the floor, and then it switches to green. So everybody, like the main street, can keep green, keeping green. I just kept it symmetric, so every street is the main street kind of. Basically, the last street that had a car passing basically stays green until the other side there's a car. And there's traffic on both sides. We just have a normal traffic light. Okay? So we have the sensors here, and these are inductive metal sensors. That's actually industrial sensors. They are so ubiquitous in industrial control that they are just called sensors. So if anybody says sensor, this, and they're everywhere. And basically, you put a piece of metal close to it, it triggers a 24-volt signal. Very standardized there, and you can just buy them in big boxes from anywhere and use them. So I abuse these sensors. Normally, I'm bringing like small toy cars, but I forgot them this time. So these batteries are the cars. So these cars, yeah. I mean, they kind of also roll. And yeah, and here's the traffic light. And this one is showing green, and this one is red. And basically, half of the application is running on one board, controlling this traffic light. So you see these I/Os are only connected to this, and these I/Os are only connected to this board. And the two, that's basically on each board runs a function block like the one I showed you, and they talk to each other. So there's also a fallback mechanism. If I pull the plug, actually there's an old code mesh talk where I demoed this, then there's a fallback application, and both get yellow blinking. So it's actually failure tolerant network. But I'm not showing this because I think it breaks our demo if I do this. So let's keep it simple. So what we now want is basically we want to show the state in the PLC. So normally we would show the PLC blocks here, but in order to be, so you can actually see that there's something physical happening and there's something mirroring the physical thing and it's going at the same time, we're actually showing the traffic light. So you have the traffic light state on the top and the sensor state on the bottom. So currently both sensors are not active, the batteries are elsewhere. So this one has green, this one is red. Let's say on the red side, a car is approaching. And you see the sensor triggers, and it gets green. Let's say on the other side also there's traffic. So traffic on both sides. Actually, the sensors are not showing anything. It's not doing anything. I think we need to reload it. Yeah, much better. Thank you for noticing. I probably would have like rambled on and didn't. Yeah, and you see it's moving. Oh, it's not. So yeah, you see it's moving basically. You don't see the sensor updates because we actually didn't have a session process with the state. So I basically need to go away and put it there, and then you actually see the sensors going on. So we kept it. Yeah, it was like last minute. We finished yesterday. So I had it set up in my room and we like last minute hacking, getting the traffic light right. And so, yeah, you see it's pretty responsive. As soon as the light goes on here, it happens on the screen. So probably every delay you see, it's basically the beamer. At least I just I just say so. So yeah, that's the demo. Thank you. Yeah, it worked. So let's switch back to the slides. Oh yeah, play. And now back to Claudia.
Yeah, I'm just gonna overview very shortly some Elm fundamentals. So what was going on back there was that the Cowboy server was communicating with Bullet to the Elm side, and the Elm side is updating in real time, as you see, with some SVG in. So Elm fundamentals. We have a few concepts which are not really that common in languages, like signals. I mean, you have reactive extensions, but in other languages, but you rarely have a language that's totally based on functional reactive. Then you have the fold P, which is a fold from the past, which is where Elm keeps the state. Well, it's not supposed to be very descriptive now, but if you hear about it, the fold P is the key part of Elm. And mailboxes are the way in which data gets around to various components. Tasks and effects are dealing with side effects. So if you have a task, you can get JavaScript, for example, to do something for you. And if you have an effect, you can describe that in the type system. So let's talk about the fundamental piece of Elm, which is signals. Signals are a different way to think about variables. So basically, they are streams of values. If you think about how we think about variables, not in functional programming, but in normal programming, object-oriented, say, there's a lack of thought about it. We don't model it in any way. If you go to functional, then a state can be immutable, and there's some more thought about it. But there is also, for example, the closure way, the STM, so of modeling variables. So you only mutate them when you explicitly want to, and but the Elm way is a bit different. So you have the stream of values, and I can show them a picture here. So that's basically a mouse changing position and the keyboard pressing various buttons. And if you look at online at that address, there's a very new visualization that really is better. So it will show, if you click the mouse, it will show you the actual signals. So if you can do that, that would be good. And so we said there are different ways of thinking about values. So they are an explicit model for values. So you're actually when a variable is mutating, also all the variables that rely on it, that depend on it, are mutating, but they're not really mutating, but changing. And so the values get around, and they're always current. And they are also a non-awkward way of structuring callbacks. If you used Node before, you must have seen the callback pyramid. So that's never going to happen in Elm. And they are basically a wired-in signal graph, a directed acyclic graph. Like this. That's an image of it. And about the practical aspects of doing that demo, in Elm, there is no current way of directly connecting with Websockets. It's going to come probably in 0.17, but now we are in 0.16, so it's not there yet. But you could do it through native, which is not really the approved way. Or you can do it through ports and a JavaScript wrapper on the other side, which is what we did. And also the code in JSON. If you have simple JSON, you will be fine using a port automatic decoding, which will work for most types, but there's some types it won't work with, like dictionaries, so you couldn't have that. Or if you have a more complicated JSON with types that are not really supported, you can do your own custom JSON decoder, but you have to watch out for lack of documentation for now. And Simon's, who is here, Program Online, was really helpful. And now back to Per.
Yeah, I didn't leave you much time, didn't I? Well, yeah, basically, when we ask about what like encoding should we use on the WebSocket, it was basically suggested by what Elm could do that, yeah, let's do JSON because there's JSON decoding. But actually it's kind of, yeah, a little bit messy, especially if you have complicated nested JSON, like describing a whole PLC graph, then it's actually kind of looking that it's not as convenient. So you need to do lots of programming to get the nested JSON decoded. So currently we are thinking about actually, since we actually need to do some work for decoding, we could actually do something more convenient for us than JSON. And yeah, well, there would always be XML, which would be actually more type checked already if you have a DTD. And basically, we had everything in XML, which some people are already now adding to JSON. But yeah, it comes with a smiley. Not really. But there is that was actually it's called Erlang external type format, term format. That was actually German autocorrect getting in my way. Sorry about that. I will change it in the published slides. So it's Erlang external term format. So basically, Erlang has complex data structures with lists and tuples and also binaries, which are very convenient for protocols. And there's an external term format, basically encoding these complex data structures in a binary stream. And Erlang uses this, for example, if you want to store binary values in a file, or if you want to send messages between Erlang nodes. So Erlang's external term format is already going through this loop here from between the nodes, and the other side can decode it. And so this would be a convenient thing for the Erlang side because, yeah, well, it's one function call and it's built in and it's written in C basically, and it's very fast. And yeah, the weak embedded system would actually profit from it, and we could do more work on the client side. So we would look at how to decode external term format. There's something else which is very similar to external term format. It's called BERT, which is basically external term format, but a little bit reduced. So there's a reduced thing because, for example, it's no use that you actually encode a process ID when you send it to JavaScript. What would you do with the Erlang process ID? Or there are several Erlang internals that also have been to encode it, which are left off. And at the same time, back then, when it was basically the first time specified, since back then Erlang didn't have a map type, there's also a special kind of tuple list which gets encoded into something that comes out, for example, if you decode it with the JavaScript side as a map or as an object. So that might be probably the way we go, or something in between. We're actually quite free to choose whatever we want because we control both sides. And that's the next thing. So I hope I don't have a typo in this URL. So this repo is not up yet. I just typed it in before. I know my Bitbucket name, and there will be a repo there, like shortly after the talk, and the repo will be empty. But you can watch it. And because currently we just finished the demo, yeah, and we need to clean this up and actually separate the demo parts, which are entangled with everything, into the repository which is then called Elmrang, like a kind of modeled version of Elm and Erlang, and which basically should provide you the minimal thing you need to basically get Elm, your Elm code, talk over WebSocket to your Erlang node. And then we might build an infrastructure around this. It's actually, probably it would be, I think we wanted to call it Elmrang Connect or Elmrang Con. Yeah, I forgot this. There will be something on this URL, probably a little website, which actually would point you to the eventual repository. Whatever. I need to put some URL up, and I put the slide in like 5 minutes before the talk.